So we're back with the second talk. The next speaker is Matthew Lugg. He's a core team member of the Zig project. Matthew, please introduce yourself.
Hi, I'm Matthew. You might know me online as Lugg. I'm currently a student in the UK. I've been a member of the Zig core compiler team since the end of middle to end of last year. I do a lot of work on the Zig compiler itself and on like community Zig stuff. Yeah, excited to be here today.
Thank you. So before we start with your talk, you get the question. Do you want normal chat or do you want emote-only chat?
I'll take normal chat.
Normal chat? Okay, 2 normal chats up until now. So please give it up for Matthew. Thank you very much.
Okay, thank you. So my talk today is going to be on data-oriented design, which is a programming strategy that we use in the Zig compiler. I'm going to cover the strategy that we've come across to utilize it a lot in the Zig compiler and how we make that type safe. So, yep, this is me. Those are all my socials. I mean, I've already introduced myself, so that's fine. Okay, going to jump right in with a problem statement. Fast software is good. Everyone can kind of agree on that. And it's become kind of a punchline at this point. Like, people will joke about, you know, NASA went to the moon with however many kilobytes of RAM, and now I need 3 gigs to open a few tabs in Google Chrome or whatever. So there's clearly some reason that this kind of slowdown, this inefficiency can happen. And it's one thing that we should look at, that we should potentially target, is our abstractions. Abstractions aren't a bad thing, but it's possible that abstractions do harm performance in some cases, and so we should analyze them. And so that's kind of what data-oriented design looks at, is the ways we abstract memory. So to look at this, we actually want to look at kind of a model of how a computer works, very basically. So you have your CPU, which is running instructions, and you have your RAM, which contains all of your data, effectively. And the two want to communicate. The CPU wants to fetch data from RAM all the time. But the thing is, RAM is really slow on the scale of a CPU. So the CPU has a bunch of this stuff called cache in the middle, which is really fast amounts of quite small memory. So the cache is organized into lines. These will generally be basically 64-byte blocks, which can be fetched from memory. And if, when we try to fetch some memory, it's already in cache, it'll be way faster because we can fetch it straight from cache, which is about between 10 and 100 times faster, typically, depending on which level of cache. The actual structure is more complicated in this diagram, but this is a good enough mental model to think about what we're going to be doing today. So the talk's on data-oriented design. There's a couple of interesting previous talks here. There's one from Mike Acton in 2014, which I finally properly watched through the other day, and I thoroughly recommend. And there's one from our very own Andrew Kelly, who is somewhere in here, out there, which kind of goes into more depth on some strategies to apply in practice. I'm actually curious to see, can we get like a show of hands, how many people have seen one or both of these? Oh, wow, quite a few people, okay. This actually reminds me, there's a tradition I need to... That went well, I'm sorry. Could you hold back 2 seconds? Amazon next day delivery, because I got about it until the last second. Oh, yeah. Thank you. Okay. So, data-oriented design then. If I had to kind of summarize it, this is what I would say. So, programs are fundamentally things that transform data. That's not like a hot take. That isn't a theory. That's what a program does. And the thing that data-oriented design states, this is kind of paraphrasing what Mike Acton says in his talk, is that the target platform is not the abstraction we're writing. Like, when we're writing, you know, structs and things like that, that's not what the hardware is doing. And the hardware is ultimately what we should be writing our code to run for. If the abstractions we write don't lead to code that's performant, maybe it's just a bad abstraction. And so one of the most interesting things to look at is to look at our data layout, because data is the most important thing in a program. So what does this mean in practice? Well, it basically means we want to make optimal use of our cache memory. And to do that, we do two key things. The first is that we want to use as little memory as possible, because the more memory we use, the more saturated those cache lines are, the more we have to fetch stuff from main memory again, which is slow. This is also obviously just nice because having less memory usage is just a good thing. It's nice. It's also important to access memory sequentially, or at least in vaguely predictable ways. If you access 1 byte over here and then 1 byte over there, and you're jumping all over the place, then you're going to have a problem where, like, you constantly have to refetch the same bit of memory, because by the time you use it again, it's been evicted from cache. We're not going to look too much at that today. We're mainly going to focus on the first point. So we're going to look at a few kind of common strategies for applying data-oriented design first. The first, and probably the simplest to generally do, is structure packing. So when you're working in languages like C, fields that you give have a certain natural alignment. So for a U16, like a 2-byte integer, that will generally require itself to be aligned to a 2-byte boundary in memory. So if you order fields weirdly, you can see on the left here, we have like these fields ordered X, Y, Z. And that results in 2 bytes of padding in there, because Y has to be aligned to a 16-byte boundary, and so does our struct as a whole. If you just reorder those fields, storing the exact same data, you save 2 bytes. Obviously, on the scale of storing one of these, that doesn't matter. But if you imagine you have a really big struct, or you're storing loads and loads of them, this can add up. Next strategy is a thing called SOA. So SOA stands for structive arrays. The idea basically is sometimes padding is unavoidable. So the example I've written here is you have like a 2-byte integer and a 1-byte integer in a struct. That's always going to have a byte of padding. You can't avoid it. And if you have a lot of them, like in a sequence, you might intuitively want to store an array in memory. So that's what we have on the left, is where, like, if the top of that is like the lowest byte of memory and it gets higher as you go down, you have 4 bytes for one struct, 4 bytes for the next, etc. We're wasting a quarter of those bytes because they're padding. So that strategy is AOS, array of structs. If we flip that around, we get SOA, struct of arrays. The idea here is that you have a separate array for every field of your struct, which means you can eliminate that padding, which is great. The last strategy we're going to look at briefly is using indices rather than pointers. So nowadays we're typically working on 64-bit machines, which is great, but it does mean that if we're using pointers, that costs 64 bits of memory. And usually we don't need that, right? Because most sequences that we store in memory are never going to exceed the 4 billion limit that you get from a 32-bit integer. So instead, if we have a sequence and we need to reference something else in that sequence, use an index like I've done on the right here. This gives you 32 bits saved for free in this case. It also has a quite nice side effect in practice, that it makes your data trivially serializable. So if you ever find yourself needing to store your data to disk, rather than doing a complicated traversal and converting to some other format, if there are no pointers involved, you can usually just write the raw binary data out straight from memory, which is quite nice. Okay, we have done a very, very brief, like, layman summary of data-oriented design. If you want more of that, look at the talks I referenced at the start. Now we're going to look at the kind of the main strategy we've used in the Zig compiler. So DoD is actually really applicable to compilers, because a thing compilers need to do all the time is store really long sequences of values. So like, compilers are kind of notorious for using a lot of memory a lot of the time, because they need to store, when they're parsing, you need to store a big list of tokens, then later a big list of AST nodes. While you're doing analysis and code generation, you're going to store big lists of IR instructions typically. IR stands for intermediate representation. Compilers will generally translate your code through kind of different, sort of progressively lower level languages in a sense. So the obvious method for representing these things is a tagged union, which I've written out here in a Zig syntax, but a kind of C style. So you have a tag, which in this case is just 1 byte, and you have data for each tag, which is stored in a union. So the problem with this is obvious when you look at the memory layout. These plus and minus, so this is representing a source code token. These plus and minus tokens have no associated data. They are a byte of information, which is the tag. But because of the padding and the payload we don't use, we waste 7 bytes every time, which is ridiculous. We shouldn't do that. The problem gets even worse if you have bigger payloads. So here, for instance, we've upgraded our parser to support 128-bit integer literals. Now we have a 24-byte thing, and yet for plus and minus, we're storing, in this case, 2 bits of information because the tag only actually uses 2 bits. That's stupid. You shouldn't do that. So yeah, the fundamental problem with using a tagged union is that every value takes as much memory as the largest field of the union. So what can we do differently? One important observation to make here is that most state that you're using is going to be around 32 bits a lot of the time. 32 bits is a quite nice sweet spot for things like indices and things like array lengths. Or sometimes they'll be bigger, but they're pretty much never smaller. Sometimes you'll have flags, but it's pretty rare. So this leads to the strategy that we use in the Zig compiler, which we call encodings with extra data. So we effectively have 2 aggregates. The first is a list of elements. So multi-array list is the thing we use in Zig for doing structive arrays. That's the thing where you have separate arrays for every field. So we have an array of tags, which might be 1 byte or maybe a couple of bytes. And you have an array of data. And the data need to be pretty small. They're typically going to be 4 or 8 bytes. And we'll see what they're used for in a second. If you need more than 4 or 8 bytes, then what you do is you store values in this separate array called extra. This is an array of just untyped 32-bit values, we just do unsigned 32-bit integers. And that data means nothing on its own. You need the context of one of the values in LMs referencing it. Once you have that, LMs tells you how that data should be interpreted. So this kind of allows us to have encodings for variable size things. So this is an example of the token thing from the previous slide. So for storing 1 token, what you have is you have your tag. That's always there, and that's always meaningful data. And then you have that 4-byte piece of data. If your tag is plus or minus, that is wasted space. You waste 4 bytes. Sucks, but there's not much we can do there. If you have a float literal, in this toy example, those are F32s. Well, that's 32 bits. We can put that straight in the data just by reinterpreting the memory. If it's an integer, we want 128 bits, and we don't have that available. So that's when we're going to put stuff into extra. So in this case, you would want 16 bytes in extra. So you're going to want 4 elements in extra, because remember, they're 32 bits. So our worst case scenario here is wasting 4 bytes, which is a lot better than before when we potentially waste 23. Okay, we're now going to look at this actually in the context of Zig. So this is kind of an overview of some key parts of the Zig pipeline. Intern pool isn't the big star at the bottom. That isn't really a stage of the pipeline, but it's an important data structure which we're going to look at. So the bits we're going to focus on today are these 3. The AST, which is the abstract syntax tree, ZIR, which is an intermediate representation that we use based on instructions, and the intern pool, which I'll explain more later. So, okay, first the AST. So the AST is a tree, as indicated by the name, constructed of nodes. And those nodes basically are just a tag, and they have potentially some children. So if you have an int literal, so I just typed 1, 2, 3 in my editor, that has no children, there's no nested information there. If I have a negation, that's a unary operation, so there's 1 child. If you have an if statement with an else clause, you have 3 children, because you have your condition in parentheses, and then you have the body of the then part, and you have the body of the else. And something like switch might have an arbitrary number of children. It could have 200 because if you're writing a switch statement, you can have as many cases as you want typically. So this is how we might represent the AST in using this encoding. Is we have our tags on the left and the comments on them describe how you use other data. So this pretty closely mirrors the actual structure of the AST for Zig. It's not exactly the same, but it's pretty similar. So for an integer literal, we have no child nodes. There's no extra data we need. We'll just ignore so we have these fields LHS and RHS. We'll just ignore them. If you have a negation, LHS is going to be the index in our nodes array of the node that's being negated, so of the single operand. And RHS is just going to be ignored because we only have one operand. If you have add, so that's a binary operation, a binary in the sense that it has two operands, then we will use LHS and RHS. That's great, but then we have some more complicated ones. So if you have an if-else statement, then we have 3 child nodes. So we can't directly store that in LHS and RHS. So here we're going to use extra. So LHS can still be our condition, but RHS is going to index into extra and point effectively, because that's effectively a pointer. We're just using an index instead, to the nodes for each of the bodies. And switch does something even more complicated where we have like a variable amount of data in extra, right? So it first tells us how many cases there are, and then for each one, it'll have like the case item and the body. So we can look at an actual example of this. It's probably the best way to get an idea of what's going on. So this is a simple bit of syntax, meaningless code, but just an example. So you have this if-else tag as our first item. You've got items on the left and extra data on the right. So the LHS of our if-else is the condition. So that's pointing to node 1, which is an addition. But the RHS points into extra data because if-else has 3 operands, so we can't just pack them in the LHS and RHS. So extra data then references the nodes 4 and 6, which are the bodies of the, the bodies of the then clause and the else clause of the if statement. So one is a negation, one is an integer literal. We don't need to go into much depth over the full example, but the important thing is understanding how extra data is used in this context. This is a more complicated example. Again, don't need to go through the full thing by any means. The important thing to understand here is how the switch works. So we have this switch statement where the LHS of it is just, again, it's the condition, it's the bit in parentheses. But the RHS points into extra data. And in this case, we don't just interpret that as AST node indices. The first one we're going to see is the number of cases we have. That then tells us how much more data to expect. And a bit later down, like index 5 and 6 in the extra data, that's separate data. That's being used for the if-else. So it kind of shows that all of this data is just packed in together, and the numbers by themselves don't mean anything. You couldn't iterate that array and do anything meaningful with it. It only means something when you have the context of, for instance, switch making a reference to it. So this representation, don't worry, we're done with the dense memory layout thinking now. This representation is pretty memory efficient. Unfortunately, we've lost a lot of type safety here, because we have these LHS and RHS fields. They're just untyped integers. We don't know how to interpret them. We just have to follow the comments and follow the existing code. If we get it wrong, everything breaks. What if we did a refactor here and changed how something's represented and missed a use site? Then probably something would go silently wrong. That's not great. So we'd like to bring back some kind of type safety if we can. So to do this, we're going to take a look at the ZIR structure in the compiler. So ZIR stands for Zig Intermediate Representation. It's basically just a list of instructions, which might be something like add 2 numbers or negate a number or construct this value. The details don't matter too much. The point is, it's actually conceptually kind of similar to the AST in that You have a big list of things. They can reference one another. So in the AST, that's like child nodes, whereas in ZIR, it's instructions operands. And most of the elements are small, but some are really big. And so you want to optimize for the small case and not waste loads of memory in that case. So yeah, we have better type safety in ZIR. So let's quickly go over a few strategies, basic strategies for type safety here. The first one, and actually a very important one, is explicitly typed indices. So when you have something which represents an index into some list, if you just have a U32 there, it's easy to misinterpret that. If you instead construct a type that kind of wraps a U32, and which you only define certain operations on through methods or something like that, then this becomes a lot safer because the type becomes a form of documentation and it's enforced by the language. This, incidentally, is not just useful in data-oriented design. This is just a very useful pattern in general, and I highly suggest trying it out. So in Zig, we typically do this with these things called non-exhaustive enums. That's the syntax at the bottom. But you could just do a struct wrapping a U32. That works completely fine. Another interesting thing to look at is using a union for the data. So in the AST, we had these fields LHS and RHS, and they were just U32s. And we had to, if we wanted a different type, we were going to cast them or something like that. So what we could instead do is use a union and have different fields for different ways we interpret this data. So it could be a plain U32, like it could be a length, for instance, but maybe it's an index with that type we defined a second ago. Maybe it's a float for some reason. Okay, so let's look at ZIR. Every instruction has a tag, just like AST nodes have a tag, and there are a few other things it might have. One is it actually might reference an AST node. The reason for that is that we want to be able to propagate source locations for error messages. So if an error happens in semantic analysis, we want to be able to point to the location in your code where it happened. Also, we might have some references to other ZIR instructions taken as operands. So if you have an add instruction, that's going to take two other instruction indices, and it's going to add their results. And we might also have some fixed data. We might have an integer, a float, something like that. Okay. Big block of code, sorry. Best way to do it. So this is kind of, again, a toy example that's quite similar to what ZIR looks like in the actual compiler. So we have this tag, which is an enum. And in this case, it has these four alternatives, add, subtract, negate, and int literal. So the last one of those just kind of returns a fixed value, and the others are doing arithmetic. But the first thing to note here is the union in data. So it has three different fields. We have the int field, which is used if you're using the int literal tag. But then we have unnode, which stands for unary operator with a source node. So this takes, so the data here is a struct. We have two things in here. There's our operand, and there's our source node. And then we also have some binary operators. We have add and subtract. And for those, we don't have enough space because we want data to be 8 bytes in this case. But we need to store 2 operands plus a source location. So we need 12 bytes. Okay, that's fine. We'll use this third field, PL node. PL here stands for payload. So this is a payload and a source node. So the idea of a payload is basically we're pointing at an index within extra. And rather than accessing elements in extra directly, another thing we can do is have these handy little wrapper types. So on the right of the screen, you'll see this binop type. What we do is we use a little bit of metaprogramming, and we basically can kind of pretend that we're storing those binops directly. What the metaprogramming does is just packs the fields of that struct into extra and unpacks them on the other side. So we get a bit more safety this way. It's the exact same kind of memory layout as before, but it looks very different because we've made the type safety better. We don't need to access extra directly, and we can interpret our data correctly more easily. It's not perfect, though. Because suppose we had a instruction that had a variable number of operands, So maybe we had an instruction which takes like an arbitrary number of operands, could be 2, could be 10, and adds them all together. We can't just have one struct contain that information because our struct has to have a fixed size. So in this case, we'll lose type safety again. We call this trailing data. So the idea is, if you look at the bottom here, we'd have this multi-op thing, which has operands len, which we store, but then there's a comment above it explaining what data comes afterwards. And that has to come afterwards rather than being embedded in the struct because it's variable length. Okay, so that's a flaw in this. So if we step back, maybe we're doing this wrong. The way we do this in ZIR is definitely better than the AST, but it kind of seems like it might be the wrong approach because all we're doing is layering type safety on top of something that's fundamentally unsafe, right? And we're still exposing the underlying system. Maybe that's not the right thing to do. Maybe we want to hide these details. So let's talk about tagged unions again for a second. We figured out that storing them is a bad idea. They're really big, typically. You have no control over the memory layout a lot of the time. Not helpful. But they are convenient to work with, right? So in Zig, for instance, Zig has tagged unions as like a first-class type. You can switch on them and capture things from them. They have a bunch of nice syntax. They're really convenient to work with. We have other types which aren't suitable to store directly, but which are, again, really nice to work with. So we have slices. For anyone not familiar, a slice is essentially a pair of pointer and length. So in short, it's a kind of way of referencing a variable length array. So these types are really nice and we want to use them, but we don't want to use them in our internal data representation. So what if we had a translation in our API? This is where the intern pool comes in. So intern pool is a type in the Zig compiler, which is responsible for storing comp time known values, comp time meaning compile time in this context. So that also includes types, because in Zig, types are values. And as the name kind of hints, it does interning, which basically means that it deduplicates the types. So the way the API works is when we create a value, we give it an index. And if you create the same value later, if you like request the same thing, you'll get the same index back because there's some data structures internally which do this deduplication for us. So as I was saying, uses a different API kind of strategy. We don't expose the implementation. Instead, we model the API as being a translation between this index, which is kind of an opaque handle, and a convenient, but not necessarily memory efficient type, in this case called key. We still use the same actual representation, excuse me. We still use the same representation for actually storing this data, because it's a good representation. It's memory efficient, it's fast, it's serializable, it has all these nice properties. But it's not a nice thing to expose to the programmer. So we don't. It's invisible to the API users. So this is kind of what that looks like. Is on the left here, we have the tag, which is a property of the like internal implementation and the way we store the data long term. We still have these 8-bit tags. A few examples are on here. We have like a tag for an unsigned integer type, one for a signed integer type. We have one for an integer value, which has the type U32. We have a bunch of these. These are just a few examples, though. But then we have the key type, which is not at all memory efficient. For instance, at the top here, so union enum is how you write like a tagged union in Zig lingo. And then at the top here, we have this int type, which immediately has like a signedness field, which is basically a bool. And storing bools in a struct is like a bad thing for data-oriented design. Like you don't ever want to store that because you're just wasting loads of memory for no reason. But in this case, it's fine because we are never going to store keys. They're just our API boundary. And we have the same kind of thing for integers below. So in this case, the integer also has a type. So it contains another index. There's kind of a nesting happening here. But yeah, the point is you have this convenient, like easy to work with representation. And then the intern pool API is just these two functions, which convert in one direction or the other. So the top one, you give it a key, which you can construct however you want, and it will spit you back an index. It might be an existing index if the type already, or the value already existed somewhere, might create a new one if needed. The exclamation mark and the allocator.error is just how you write errors in Zig, because this might do allocation, so it might fail. And then the second function translates the other way. You give it an index and it gives you back a key. So at no point here are we exposing the messy stuff that's happening under the hood, which means we don't need to worry about that across the code base. Like if you make a change to how the intern pool is representing things, that change isn't too sweeping of a change now. All of your changes are localized within the implementation of intern pool. So yeah, API users only have to deal with key. And actually, this makes for a really nice API. This is just a random example that I just ripped from the code base, basically. It's just a function that takes in an arbitrary intern value and tells you whether it's a constant pointer type. And so it's just doing index to key to get our nice representation, and we do a switch. And we can capture out the result, we can look at it. Yeah, you get a really nice API from this. This is a bit of a tangent, but it's an interesting tangent. The way we do interning is kind of fun. So we have this field here in the intern pool called map, which is a hash map from void to void. So you probably look at that and go, well, that makes no sense. That just seems like, I guess it seems like a really expensive Boolean. But what's actually happening here is this is a type in the Zig standard library called an array hash map, which stores an array of keys and an array of values and all of the hash map metadata. So it will store hashes, it will store all the lookup stuff it needs. And the API of array hash map lets us define custom functions for hashing inequality based on where we are in that array. But at that point, we don't need to use that array of keys and values. Once we have the index, we can deal with those ourselves, which is kind of what we do here. This isn't relevant to the type safety at all. It's just an interesting data-oriented thing we do. I'm not going to go into more depth on it now because it's not too important, but it is interesting. Okay, so what have we done here? We've looked at the strategy we use for data-oriented design in the Zig compiler. That's encodings with extra data. We use it for all kinds of things, and we're kind of using it more and more over time, really. And it's a really nice pattern, but it has a problem, which is that it's naturally not type safe. And we can incorporate some strategies to regain type safety. Typed indices are really important, and we can do things like using a union and accessing extra data through structs, but these don't quite work well. So it turns out the best way to do this is just to provide a type-safe API. Not exposing the implementation in this case is a really good way of doing it, because you end up being able to work with the strengths of your language, whilst also at the low level working with the strengths of the hardware. Yeah, that's all.
Thank you very much, Matthew. Please join me on the armchairs and let's have a little bit of a Q&A. So I see already some questions from the audience. So August is going to bring you a microphone. There you go.
Yep.
Thank you for the nice talk. But when you make type safe, you lose something in the sense if you don't access all fields of your structure, then you still unwrap everything, right? Or am I missing something?
No, yeah, so that is, in theory, a downside. I haven't looked at the generated code for this, but I would suspect that the optimizer's pretty good at dealing with that. The required optimization would essentially be inlining the access and then just noticing that certain fields aren't used. And I think it would probably do that in a lot of contexts. I might be wrong, though. That for sure could be a downside, yeah.
Thank you.
We've got someone all the way up there. Go, August, go.
Yeah. So basically, the extra array works as a bump allocator. Why don't you just use the bump allocator directly to store the data?
The thing with using a actual bump allocator is that you can't use indices anymore, right? Because at that point, you're working with an arbitrary blob of memory, and so you have to use pointers within it. And pointers, for reasons briefly mentioned there, are not ideal to use in structures. They're bigger than you need them to be, and it means that your data isn't relocatable. Indices are more compact and can be nice for things like serialization.
Okay, thank you. Any other questions?
One here.
Let's watch August do some route planning.
Okay. I have a question. So on the diagram earlier in the presentation, the intent pool was drawn after the Zig intermediate representation step. Is it used only after, or is it used generally even for the AST?
So the intern pool is used after you generate ZIR, kind of from every point in the pipeline onwards there, but it's mainly used by semantic analysis, which is the pass that acts on ZIR.
Why? Couldn't it be used for storing the AST as well?
They're different goals. The intern pool is only there to store like Zig values. That's its job. We are essentially using the same, we're using the same storage strategy for the AST. And the only reason the AST and in fact ZIR don't use something more akin to the intern pool's API is because we've been learning this, we went along, right? The AST was, this stuff was all mostly done by Andrew Kelly. And the AST was like his first time trying out this DoD strategy, I believe. And it kind of shows. It's not the nicest code to work with. ZIR, he's kind of figured out how to make it a bit safer, a bit nicer to work with. And intern pool is kind of when we finally nailed it down how to do it. So hopefully in the future, we'll be able to upgrade the other parts of the compiler to use an API more akin to intern pool with the nice things that brings.
Cool, thank you.
One last question.
Whoever you want, pick your favorite.
Could Zig help more with this kind of pattern? Because I tried to beat myself and I think a bit cumbersome. I was wondering in particular if Zig could have support for a small slice type, where you could have a slice where the pointer and the length are backed by smaller integers, and you still have the slicing syntax and so on.
So where you're suggesting a slice type with a smaller size.
Yeah.
The problem with that is alignment, because the pointer still needs to be your system's native pointer size. So once you have that field, if you also have a size in there, you end up needing padding anyway, which brings it up to twice the size of a pointer. So you can shrink the length field as much as you want, but as long as it's there, the slice as a whole still has to be twice the size of a system pointer, unfortunately. Because you need padding bytes to align the pointer correctly.
When you could have two U32.
If you have two U32, then you can't represent the pointer correctly, right? You can't assume
It's not the pointer, it's like an index, but it's a...
Oh, you're saying have an index, so have a built-in type, which is...
on an index.
There's not really much reason for that to need to be a built-in type, because the thing that's actually being operated on always is a pointer. Like when you have an index and a length, you do eventually have to turn it into a pointer. And so it's not like you'd really get much nicer syntax out of that, because you'd have to tell it what buffer it's indexing into. So it would kind of end up being the same thing.
Yeah. Good.
Thanks. That's okay.
Okay, thank you very much. So, thank you, Matthew. That was a great talk. And if anybody has more questions, because I think I saw some more raised hands, please feel free to find Matthew outside after we're done here and, chat him up. So, please give it up for Matthew. Thank you.